Something truly monumental is unfolding at Google. In an astonishingly short span, they've unveiled not one, not two, but three groundbreaking artificial intelligence innovations. Each targets a completely different domain, from abstract research to real-world environmental monitoring. Yet they share a profound common goal: to push the boundaries of what AI can achieve, making it more autonomous, more human-like, and ultimately, far more capable in high-level tasks. We're talking about systems that can write deep, intricate research reports that outmaneuver leading competitors, AI agents that can build production-ready machine learning pipelines from scratch, and even an intelligent mapping system that can chart the entire Earth like a perpetually updating virtual satellite. The implications are staggering. Let's dive straight in with the first breakthrough, a system known as Test-Time Diffusion Deep Researcher, or TTDDR. The name might sound complex, but its function is elegantly simple. It represents a significant leap towards AI behaving like a genuine human researcher. Think about how most AI agents currently generate reports. They often act like a collection of tools cobbled together, lacking the intuitive, iterative thought process of a human. Real researchers don't just instantly churn out a final document. We plan our approach, meticulously search for information, refine our understanding, draft initial versions, rewrite, gather crucial feedback, and then reshape everything until the report is robust and solid. TTDR is engineered to mimic this very process. It conceptualizes the entire research journey as a type of diffusion, much like progressively clearing up a blurry image until it achieves crystal clarity. In this case, it starts with a rough research draft, and that draft continuously evolves and improves with every subsequent step. What makes TTDDR so remarkably clever is its ability to constantly pull in external information at every single stage of the process, using an advanced retrieval system. This means it's not confined to a fixed database or internal knowledge. It's always learning and refining the draft as it goes. This dynamic approach prevents it from losing context or fumbling the flow, a common pitfall for many other AI agents. Each draft version serves as the solid foundation for the next, mirroring how we naturally construct a complex piece of writing. Google put TTDDR through its paces on some incredibly challenging benchmarks, tasks that demanded multi-step reasoning and deep, extensive searches. We're talking about intricate research questions that can't be answered with a simple summary. And the results? TTDDR didn't just perform well. It decisively beat OpenAI's deep research system almost across the board. In long-form reports, TTDDR emerged victorious in nearly 3/4 of head-to-head comparisons. Even on datasets requiring shorter, more concise answers, it still outperformed OpenAI by close to 8% in certain scenarios. It also consistently ranked higher in terms of helpfulness and comprehensiveness, especially for those multi-hop, layered tasks where most other agents tend to fall apart. The system itself operates through 3 major stages: meticulous planning, iterative searching, and finally, comprehensive report writing. Each of these stages is powered by its own set of smaller, specialized agents and workflows, which are further enhanced by something Google calls self-evolution. This ingenious mechanism allows each component of the pipeline to learn from previous errors and intelligently reconfigure itself to improve performance. They can run these processes in parallel, sequentially, or even in continuous looped cycles, constantly refining their output. To be clear, the Test-Time Diffusion Deep Researcher has demonstrated a superior ability to follow complex ideas reliably, maintain focus through lengthy reasoning steps, and significantly reduce mistakes. While OpenAI's system showed a slight edge in one very specific benchmark, across the full spectrum of in-depth research tasks, TTDDR displayed consistently stronger overall performance. But Google's advancements don't stop at research. Let's move on to something equally revolutionary: MLE Star. At first glance, it might appear to be just another machine learning tool, but make no mistake, it operates on an entirely different plane. This is a full-blown AI agent capable of taking a machine learning task, whether it's classification or regression, and building out real, functional Python code that not only works but is also designed to win competitions. The core difference here is that MLE Star doesn't simply guess or rely on outdated methods. It begins by intelligently searching the web for the most relevant and competitive models. Not what was popular in 2017, but the cutting-edge solutions like Vision Transformer or EfficientNet, precisely tailored to the specific data type at hand. So, Instead of defaulting to legacy methods or habitually sticking to familiar libraries, it dynamically adapts to the unique requirements of the task in front of it. But what truly makes MLE Star so powerful is its sophisticated code refinement process. After generating an initial basic pipeline, it meticulously tests each component to pinpoint exactly what contributes most to performance. It then zeroes in on the most impactful elements and starts refining from there. Perhaps it's a critical piece of feature engineering, or maybe it's the way the model ensemble is constructed. Once it identifies that key area, it iteratively experiments with different strategies, constantly reflecting on the results of past runs. And yes, it keeps looping that refinement process until it hits optimal performance. When it comes to model ensembles, MLE Star goes even further, creating its own unique merging strategies rather than relying on simple voting mechanisms. It proposes several candidate models, then intelligently merges them using complex ensemble logic it generates on the fly. It then continuously tweaks that logic based on results from earlier runs. This isn't just cookie-cutter voting. It's a dynamic agent-style optimization. To prevent common issues with large language model-generated code, Google has integrated 3 crucial safety nets. First, a dedicated debugging agent is in place to handle execution errors. Second, a data leakage checker diligently scans for common security vulnerabilities, like accidentally using test data in the training phase. And third, a data usage checker ensures that the model actually utilizes all the data sources provided. You'd be surprised how many models might unintentionally skip over important JavaScript object notation files or ignore crucial satellite imagery just because comma-separated values might appear easier to process. Google rigorously tested MLE Star on Kaggle tasks from a benchmark known as MLE Benchlight. The results were astounding. MLE Star earned medals in almost 2/3 of the competitions, with over 1/3 of those being coveted gold medals. Compared to the previous best baseline, which only managed medals about 1/4 of the time, this represents an enormous leap in capability. They also conducted a deeper analysis. For instance, they examined how MLE Star chose models in image classification. While older agents often defaulted to established neural network architectures, MLE Star consistently leaned towards newer, more effective options without needing extra prompting. Remarkably, when human experts did provide additional assistance, like manually suggesting a specific multi-layer perceptron, MLE Star adapted immediately and seamlessly integrated it into the training pipeline. It also proved exceptionally adept at correcting hallucinated code, cases where the large language model might mistakenly try to normalize test data using its own statistics. That's a fundamental error in machine learning, and MLE Star consistently caught it. The same goes for forgotten data. It double-checked task descriptions and ensured everything was pulled in and used appropriately. So this goes far beyond simply generating code. MLE Star handles the entire machine learning process with sophisticated built-in checks, intelligent refinement, and genuine flexibility. And the best part? The core codebase is open source, meaning anyone can begin using it right now through Google's Agent Development Kit. Now let's zoom out far beyond individual tasks to something truly planet-sized. This final innovation is called Alpha Earth Foundations, or AEF, and it's DeepMind's answer to a problem that has plagued us for decades. How to effectively make sense of the sheer deluge of data pouring in from Earth observation satellites, climate models, drones, in-field sensors, radar scans, and countless other sources. There's simply too much raw data and far too little labeled data to match it effectively. Satellites can provide images of floods or forests, but unless you have accurate ground truth labels, it's incredibly difficult to use that data for precise real-world mapping. That's precisely where AF comes in. It's essentially what they're calling a virtual satellite, an AI model that doesn't rely on waiting for the next satellite pass. Instead, it creates comprehensive global geospatial layers from all the existing Earth observation data we have, transforming them into what they term embedding fields. These fields boast an impressive 10 by 10 meter resolution, cover the entire globe, and even extend all the way back to 2017. Every layer functions like a high-density data tile, representing everything from climate patterns to terrain, vegetation, and infrastructure, you name it. What's truly wild is how incredibly compact this data is. Each patch is encoded into a tiny 64-byte vector, which is an astonishing 16 times smaller than even the most compact traditional models, yet without any loss in performance. It works seamlessly with past records, handles missing information without breaking down, and can generate remarkably accurate maps for any date you require. If a region had cloud cover or missed satellite passes, AEF still provides a coherent map by intelligently using learned associations and fusing data from multiple modalities. Under the hood, AEF employs a revolutionary spacetime precision architecture. This means it simultaneously processes data across three critical axes: space, time, and resolution. It combines powerful attention mechanisms for spatial patterns, temporal layers to pull in historical data over time, and multi-resolution blocks that ensure fine details remain exceptionally sharp. What's more, it even incorporates geotagged text from sources like Wikipedia, seamlessly blending raw observational data with rich, real-world semantics. This model is already actively being deployed across the globe. Organizations like the United Nations, Brazil's Map Biomas project, and various scientific teams are harnessing AEF to monitor critical environmental changes that often go unnoticed. They're tracking forest loss, overseeing agricultural development, mapping urban sprawl, and studying subtle shifts like the slow drift of sand dunes or the gradual shrinking of wetlands. A key feature enabling this widespread utility is AEF's ability to generate maps for any desired date without waiting for new satellite updates. The system pulls from existing data, intelligently fills in any blanks where needed, and produces detailed, up-to-date views of regions that might otherwise be missed. There's no lag, no need to rely on perpetually cloud-free scenes, and no painstaking manual stitching together of disparate datasets. Everything comes together in one coherent, analysis-ready map, available on demand. So, instead of needing to build a new, specialized model for every single mapping task, governments and researchers can now simply plug into AEF's global annual embedding layers directly within Google Earth Engine. This powerfully levels the playing field for smaller organizations and research teams that don't have access to massive GPU clusters or enormous dedicated teams. Looking forward, DeepMind aims to scale AEF to even finer resolutions, integrate more text and local knowledge, and ultimately evolve it into dynamic Earth twins, essentially living digital models of our planet that update in real time. These three innovations, the self-improving deep researcher, the autonomous machine learning engineer, and the virtual satellite of Alpha Earth foundations, are more than just impressive individual breakthroughs. They signal a profound shift in Google's approach to AI development, pushing towards agents that are not only intelligent, but also capable of learning, adapting, and even evolving autonomously. The future they paint is one where AI takes on increasingly complex, multifaceted roles, redefining the very nature of work and our understanding of the world around us. What do you think is the most transformative, or perhaps even the most dangerous, potential use of any of these groundbreaking advancements? Share your thoughts in the comments below. If you found this information valuable, please hit that like button and subscribe for more insights into the future of AI. Thanks for watching, and we'll catch you in the next one.